Logarithmic differentiation. In this video, I will present an important example of implicit differentiation called logarithmic differentiation. If you had forgotten how to differentiate implicit functions, then before starting this video, you may need to review this topic by watching the video that appears in the upper right corner. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. So far we learned to differentiate all the old families of functions that we knew from algebra, trigonometry and precalculus, and we run into two basic rules, the power rule and the chain rule. The power rule applies when we run into a function of x being raised to a power that is a constant. An example of this is given as follows. The derivative for the exponential function applies when we have a constant being raised to a function of x. An example of this is given as follows. Obviously, we can combine these rules with the chain rule. Let's see two examples. But, of course, this does not cover all the types of functions that we might see. There are many functions for which the rules and methods of differentiation we have seen so far are not sufficient. For instance, how would we compute the derivative of a function of the form? We notice that there are functions of x in both the base and the exponent. That means we can't use our normal rules. We cannot differentiate by using the power rule because its exponent is a function, not a number. We cannot differentiate by using the exponential rule because its base is a function, not a constant. The derivative of this function requires a technique called logarithmic differentiation. The key point here is the fact that logarithms allow us to change powers by products. Therefore, the logarithm can provide a simpler method of solution. Let us see how logarithmic differentiation works. Given a function of the form, the derivative is found using logarithmic differentiation as follows. Step 1. Apply the natural logarithms of both sides of the equation and simplify the right-hand side as much as possible using the general properties of logarithms. Step 2. Apply implicit differentiation with respect to x. Step 3. Solve the resulting equation for y prime. Let's see how it works. We notice that there are two functions of x in both the base and the exponent. In other words, this function has x in the base and the exponent. So we can't use the normal rule. We must use logarithmic differentiation. Step 1. Take the natural logarithm of both sides, and after applying the exponent rule for logarithms, the right-hand side of the equation is a product function that can easily then be differentiated. Step 2. Differentiate implicitly with respect to x. We use the product rule on the right side and the chain rule on the left side. Step 3. Solve the resulting equation for y prime. Take a look at the item B. Both the base and the exponent are functions of x. In this case, we use logarithmic differentiation, and there is no other way to do it. Step 1. Take the natural logarithm of both sides, and after applying the exponent rule for logarithms, the right-hand side of the equation is a product function. Step 2. Differentiate implicitly with respect to x. We use a chain rule on the left side. We use the product rule on the right side and then chain rule. Solve the resulting equation for y prime. Let's see another example. Step 1. Take the natural logarithm of both sides, and after applying the exponent rule for logarithms, the exponent changes to the product on the right-hand side. Step 2. Differentiate implicitly with respect to x. We use the chain rule on the left side. After applying the product rule for differentiation on the right side, we apply the chain rule on the first term of the right side. Step 3. Solve the resulting equation for y prime. You should try to solve the next examples yourself and then check the answers.